All right, here is torque and rotation problem number 2. So we've got a toy top with a spool of a diameter of 5 centimeters that has a moment of inertia, and it gives it to us right here of 3 times 10 to the negative fifth kilogram meter squared about its rotation axis. It says to get the top spinning, its string is pulled with a tension of 0.3 newtons. And then the question asks, how long does it take for the top to complete the first 5 revolutions? So again, trying to figure out what's going on. Some of these problems are a little bit goofy. Let's go ahead and start writing our givens. That'll give us a place to start. So it says that the spool, so we're talking about, like, if you look at the top from above, you may have played with a top like this before, maybe not. It's got, like, on the handle of it, it's got a circle that you can kind of pull a ripcord, and maybe the top is bigger and it's like up here. So I'm looking at it from above, and there's string that's wrapped around and around and around here, and then you're going to pull it off like this. And so we're talking about this right here as the tension force, Ft, okay? And that's a force that's being applied a certain distance away from the center of the axis. So this is our radius that we're talking about, okay? Sometimes, like I said, it's a little bit hard to figure out what the story is, but again, looking from the top, you can kind of imagine pulling that string perpendicular to the circle. Okay, so let's go ahead and write down our givens and see where this goes. So it says the spool has a diameter of 5 centimeters. So there are a couple pieces in here. First one is that it says diameter, right? So that's a big deal. And we don't really care about diameters, we care about radii. So we're gonna have to divide that by 2. And also this is written in centimeters. Everything that we're gonna do in terms of the moment of inertia is in meters. So we need to go ahead and convert that also into meters. So I'm going to just write that the radius is, so it's going to be 0.25 centimeters or 0.025, meters for our radius. So that's the first little piece of given information. It also says that our moment of inertia is 3 times 10 to the negative fifth kilogram meter squared. I don't know if in the papers that I gave you, it gave that in kind of a weird funky thing. Sorry about that. I noticed this morning when I was working through it that the notation got a little goofy there, so I apologize if that happened. But that is our moment of inertia, so we don't have to worry about any of the equations or any of that because it just flat out gives us the value, okay? And then it says the string is pulled with a tension, so that's my Ft of 0.3 newtons. And then it wants to know how long it takes, so it's looking for a time. I guess I'll write that in orange for our unknown. How long does it take to complete its first 5 revolutions? So again, they're kind of masking exactly what's going on in terms of what that is. But 5 revolutions is going to be a measure of angle, right, or angular displacement. So really what we're talking about is a delta theta, but we don't want it in revolutions, we want it in radians. So we're going to, just like we did on the last problem, convert from revolutions to radians. So we're going to say 2 pi radians in 1 revolution, which is going to be 10 pi radians, which is 31.4 radians. So that's your angular displacement, okay? And now we're going to kind of play the same game we did on the last one. So in order to get this thing to spin, we have to apply a torque, right? And the torque can be calculated by the force applied times the distance away, or excuse me, I should use R here, the distance away from the axis of rotation, okay? So that's going to be our 0.3, or excuse me, yep, our 0.3 newtons for our force, and then our 0.025 for the distance apart, the distance away, which is the radius of the circle. So when I do that, I'm just going to plug some numbers in here, and I get 0.0075 Newton meters for the torque. Using that, just like we did in the last problem, again, because we're looking for a time, just disappeared. It's strange. We're looking for a time, so we're going to need to use kinematics. We've got theta, we're looking for time. We need an alpha in there. That's really what we're going for. So we also know that torque is equal to I alpha. So we can say that alpha is equal to that torque that we just found divided by the moment of inertia that they give us in the problem. And so we can find here that alpha equals, I'm going to plug in, so I'm plugging in 0.0075 divided by 3 times 10 to the negative fifth, and we get an alpha of about 250 radians per second squared. And now we just need to use my favorite of the rotational kinematics equations. Delta theta is equal to omega initial t plus 1/2 alpha t squared. It's starting at rest, I am assuming. I guess it doesn't explicitly say that, and I apologize for that. Generally, if it doesn't say that it's moving, it's not moving, right? And so then we've got all the other things we need to solve for time. You've done this in translational motion a million times. Maybe that's exaggerating, but a lot, right? So this is going to be 2 delta theta divided by alpha. And using that, you can go ahead and solve and find that the time it's going to take for that acceleration is really just half a second. It doesn't take very long at all. All right, we'll see you for one more.